All right, let's talk about a challenge that's at the heart of process engineering. It sounds super simple, but wow, is it packed with complexity. We're talking about figuring out just how big a pipe needs to be to get a liquid from point A to point B. Let's dive in.
So, here it is, the big question. You've got some fluid, you need to move it. How big is the pipe? Seems easy enough, right? You just pick one that can handle the flow. But, the real answer is, it's complicated. And if you get it wrong, the consequences can get really expensive really fast.
And this lays out the stakes perfectly. If you go too small, you're just burning cash on energy trying to shove all that fluid through. Not to mention, you're literally sandblasting the inside of your pipe, causing erosion and a ton of noise. On the flip side, go too big, and you've just thrown a pile of money away on steel you didn't even need. Even worse, the fluid can slow to a crawl, letting solids drop out and clog the whole thing up. It is a classic engineering tightrope walk.
So here's how we're going to break this down to find that perfect size. We're going to look at the main problem, then walk through 3 key constraints: the physical speed limit of the fluid, the cold, hard economics of it all, and finally, the stability of the entire system. Then we'll see how it all comes together.
Okay, first up, the problem itself. Because sizing a pipe is about so much more than just hitting a target flow rate. It's really about balancing safety, efficiency, and reliability for the entire life of a plant. So let's get a formal definition on the table. When we say process line sizing, what we're really talking about is this engineering practice of finding the optimal diameter. And that sweet spot is where 3 things are perfectly balanced: how fast the fluid is moving, how much pressure you lose from one end to the other, and, of course, how much the whole setup is going to cost you.
Our very first constraint is a hard and fast physical limit. You just can't push fluid through a pipe too quickly without things starting to go very, very wrong. Think of this as the system's absolute non-negotiable top speed.
I love this analogy because it's so perfect. You know what happens when you floor it on a gravel road, right? Rocks fly everywhere, your tires get chewed up. Well, it's pretty much the same thing inside a pipe. Go too fast, and the fluid starts to scour the inner wall. It's a process called erosion corrosion, and over time, it just wears away the metal, which can lead to leaks and eventually failure. So how fast is too fast? Well, it all depends on what the pipe is made of. We have industry standards like NORSOC that give us some really solid guidelines. For your standard carbon steel pipe, you want to keep the speed below about 4 meters per second. This helps preserve the protective layer on the inside. But for tougher stuff, like stainless steel, you can push it a bit faster, maybe up to 6 meters per second, because it's just more resistant to that scouring effect. Going past these numbers is really playing with fire. All right, let's move on to our second constraint, and this is a big one: money. As with pretty much any engineering decision, this all comes down to a financial tug of war. We're talking about upfront costs versus long-term running costs. On one side of the rope, you have your capital expenditure, or CapEx. That's the money you spend right now on the pipe, the valves, the supports, and it's simple. Bigger pipe equals more steel, which equals a bigger bill. Pulling on the other side is your operating expenditure, or OPEX. That's the cost of electricity to run your pumps for the next 20 or 30 years. A smaller pipe means more friction, which means you need a bigger pump and you're going to have a higher energy bill forever. So what happens when you run all the numbers and balance those 2 costs over the entire life of the plant? Well, you almost always land in a very specific velocity range. For most typical liquids, this economic sweet spot is somewhere between 1 and 3 meters per second. It's not a law of physics, but it's the zone where you get the most bang for your buck.
Okay, last but definitely not least, we have to remember that this pipe doesn't exist in a vacuum. It's one piece of a huge, interconnected system, and its design has to make sure that whole system stays stable and happy.
This really boils down to 2 things. First, after all the energy losses from friction, does the fluid arrive at the end with enough pressure, enough oomph, to do whatever it needs to do next? And second, is the flow itself stable enough to stop things from going wrong inside the pipe along the way?
And this is where you have to think long-term. An engineer can't just design for a perfectly clean, brand new pipe. You have to account for something called roughness aging. Over years and years of service, the inside of that pipe gets rougher from a little bit of corrosion or scaling. That extra roughness creates more friction, which means more pressure drop. And more pressure drop means higher pumping costs, which is exactly why our economic calculation has to look at the pipe 20 years from now, not just on day 1. But, and there's always a but, right? There's that flip side to velocity. We know going too fast is bad, it causes erosion, But going too slow can be just as disastrous. If your velocity drops below a certain point, what we call the critical velocity, any solids mixed in with the liquid will just start to fall out of suspension, settle at the bottom, and eventually you'll get a clog that shuts the whole process down. So, as you can probably tell by now, this isn't just about plugging some numbers into a simple formula. It's a really sophisticated judgment call. It's about taking all of these competing factors and finding that one single optimal solution. So let's just recap that three-way balancing act. The engineer has to pick a diameter that keeps the velocity low enough to avoid erosion, but also high enough to be economical and keep solids from settling out. And they have to do all of that while making sure the pressure drop isn't so great that the equipment downstream can't do its job.
And that brings us to this final thought. It's not just a science. It's about having a deep understanding of the physics, the economics, and the long-term life of the system. It really, truly is an engineering art form. And why does all this matter? Because getting this right is the invisible foundation of any industrial process that is safe, reliable, and profitable.